When you look up at a clear night sky far from city lights, the luminous arch of the Milky Way can feel impossibly vast. A sprawling wheel of several 100 billion stars, stretching across 100,000 light-years of space, it represents everything we have ever observed with the naked eye. For most of human thought, this colossal city of suns was assumed to be the entirety of physical existence. But modern astrophysics reveals a jarring reality: our galaxy is not the cosmic ocean. It is merely a single drop of water suspended within an expanse so immense that human intuition breaks down entirely. To comprehend the true scale of the cosmos, we must look beyond our stellar home and measure the Milky Way against the true structure of reality. If you enjoy deep, immersive explorations of real astrophysics and the extraordinary engineering that expands our horizon into the cosmos, please consider liking this video and subscribing to the channel. Your support helps us create more long-form documentaries that uncover the quiet mechanics of the universe. Milky Way as a measurement baseline, light travel scale, and stellar density. To measure the overwhelming vastness of the cosmos, we must first establish a rigorous baseline scale using our own galactic home. The Milky Way is a barred spiral galaxy of immense proportions by human standards, featuring a flattened stellar disk spanning approximately 100,000 light-years from edge to edge. Within this sprawling disk, an estimated 100 to 400 billion stars revolve around a central gravitational anchor. When we look up from our vantage point on Earth, positioned roughly 27,000 light-years from the galactic core along the inner edge of the Orion Cygnus arm, the galaxy appears as a continuous dense band of white light arching across the night sky. This optical phenomenon is the direct result of viewing the thin disk of stars edge on from within. Every single star ever recorded by human observers prior to the invention of modern optical telescopes resides well within this local galactic neighborhood. The true physical scale of the Milky Way becomes apparent when we translate spatial distance into light travel time. Light, traveling at the cosmic speed limit of 300,000 kilometers per second, takes over 8 minutes to reach Earth from the Sun and roughly 4 years to reach Proxima Centauri, our nearest stellar neighbor. To cross the full diameter of the Milky Way's main disk, a single beam of light must travel uninterrupted for 100,000 years. If an ancient ancestor of modern humans had dispatched an optical signal from the far western edge of the disk during the Pleistocene epoch, that light would only now be arriving at the eastern boundary, the central bulge of our galaxy. A dense spherical swarm of older stars surrounding the supermassive black hole Sagittarius A extends over 10,000 light-years in diameter. Surrounding the visible disk is a vast, diffuse stellar halo, spanning more than 200,000 light-years, housing ancient globular clusters that orbit the galactic center like slow, glowing satellites. Stellar density varies dramatically across this colossal structure, dictating the local physical character of deep space. In the solar neighborhood, stars are separated by immense empty expanses, averaging a distance of roughly 5 light-years between neighboring systems. This spatial separation is so enormous that if two galaxies identical to the Milky Way were to pass directly through one another, the odds of any two individual stars physically colliding are practically zero. However, as one approaches the galactic core, stellar density climbs exponentially. Near Sagittarius AR, millions of stars are packed into a region only a few light-years across, creating a gravitational environment where stellar separations shrink to light days or light hours. Here, the night sky on an imaginary planet would shine with the collective brilliance of 100,000 full moons, illuminated by the sheer concentration of radiant suns. Yet, despite this vast concentration of mass and light, the Milky Way consists primarily of empty space. If we perform a conceptual scale reduction and compress our entire solar system out to the orbit of Neptune down to the size of a single millimeter coin, the Milky Way disk would still stretch across a distance of over 22 kilometers. On this same scale, The distance between neighbouring stars would be equivalent to several hundred meters of absolute vacuum, with nothing floating between them except sparse interstellar gas and microscopic dust grains. The Milky Way is not a solid object, but a whisper of luminous matter suspended in a near-perfect vacuum. Establishing this immense physical baseline is essential for human cognition, because only by realizing how overwhelming our Husum galaxy is can we begin to grasp the frightening reality of the cosmic scale beyond it. As we look toward the outer limits of the galactic disk, the stellar population thins rapidly into the dark expanse of the circumgalactic medium. The gas and plasma surrounding our galaxy extend hundreds of thousands of light-years into the cosmic void, forming a warm gaseous halo that acts as a reservoir for future star formation. This halo marks the true physical reach of the Milky Way's direct gravitational dominance over ambient matter. For decades, early astronomers believed this vast halo represented the absolute boundary of everything that existed, viewing the distant nebulae seen through early telescopes as small clouds of gas drifting within our own galactic borders. The realization that the Milky Way was merely an isolated system surrounded by an endless abyss of outer space represented one of the most profound shifts in human scientific history. The structural architecture of the Milky Way is further refined by its spiral arms, the Perseus arm, the Scutum Centaurus arm, and minor spurs such as our own Orion Cygnus arm. These arms are not rigid mechanical structures like spokes on a bicycle wheel. Rather, they are density waves that move through the galactic disk, compressing interstellar gas and triggering brilliant bursts of new star formation. As massive blue stars are born within these compressed shock fronts, they burn through their nuclear fuel rapidly, exploding as supernovae before completing a single orbit around the galaxy. This continuous cycle of birth, nuclear synthesis, and explosive death enriches the interstellar medium with heavy elements, providing the raw chemical building blocks necessary for rocky planets and living organisms. When we calculate the mass of this entire dynamic system combining hundreds of billions of stars, interstellar dust clouds, gaseous nebulae, and the central supermassive black hole, we arrive at a stellar mass equal to roughly 60 billion suns, and a total gravitational mass including dark matter exceeding 1 trillion solar masses. To human minds bound to the surface of a single terrestrial planet, these numbers represent an incomprehensible magnitude of matter and space. The Milky Way is an empire of stars so vast that a human spacecraft traveling at conventional rocket speeds would require hundreds of millions of years just to escape its local spiral arm. It is our entire physical reality, the nursery of our species, and the supreme ceiling of human spatial experience. However, from the perspective of modern extragalactic astrophysics, this colossal empire of stars is nothing more than a local starting point. The moment we peer past the outer limits of the circumgalactic halo, the Milky Way ceases to look like a cosmos and begins to look like a single, solitary particle. The vast light travel distance of 100,000 light-years, which once seemed to defy human imagination, becomes a microscopic unit of length when placed alongside the structural hierarchy of the universe. To take our first step past this local baseline, we must cross the dark intergalactic gulfs that separate our home system from its immediate neighbours, where the true proportion of galactic existence begins to unravel. Consider the dynamics of gas dynamics within the spiral arms. As interstellar gas clouds enter a density wave, the sudden increase in ambient pressure causes the cold hydrogen gas to collapse under its own weight, forming massive star-forming complexes such as the Orion Nebula. These nurseries shine with intense ultraviolet light, illuminating the surrounding gas clouds before stellar winds carve out vast bubbles in the interstellar medium. Over hundreds of millions of years, these bubbles overlap, creating a porous, sponge-like structure throughout the galactic plane where warm ionized gas and cold molecular clouds coexist in a delicate thermodynamic balance. Furthermore, The rotational mechanics of the Milky Way provide direct physical evidence of invisible cosmic components. If the galaxy's mass were concentrated entirely within its visible stars and central bulge, Keplerian dynamics would dictate that stars near the outer edge of the disk should orbit much slower than those near the core. Yet, precise spectroscopic observations reveal a flat rotation, curve, stars at the outer edge of the disk orbit at virtually the same velocity, approximately 220 km per second, as stars located much closer to the center. This persistent rotational speed implies that the visible disk of the Milky Way is embedded within a massive, spherical halo of invisible dark matter that extends out to at least 300,000 light-years, exerting a powerful gravitational grip that keeps the outer disk from flying apart into the intergalactic void. This dark matter halo accounts for more than 85% of the galaxy's total gravitational footprint. Without this invisible scaffolding, the rapid rotation of the disk would have flung stars out into deep space long ago, tearing the Milky Way apart before life ever had the opportunity to emerge on Earth. Thus, even within our home system, the visible luminous stars represent only a fraction of the underlying physical structure. The Milky Way is a complex composite system of dark mass, glowing plasma, and stellar furnaces, held together by invisible gravitational forces across a scale that exhausts terrestrial imagination. Yet, as majestic as this stellar empire appears, it is merely the first step on a journey that will take us across scales so immense that our entire galaxy shrinks to an infinitesimal point. Local group and the gravitational island paradox. Stepping beyond the outer halo of the Milky Way brings us into the intergalactic gulf of the local group, a gravitationally bound cluster of galaxies spanning roughly 10 million light-years across. In this regional cosmic neighborhood, the Milky Way is no longer an isolated titan, but one of two dominant gravitational anchors in a small archipelago of island universes. The other dominant anchor is the Andromeda Galaxy, designated M31, a massive spiral system located approximately 2.5 million light-years from Earth. Andromeda is significantly larger than the Milky Way, containing upwards of 1 trillion stars and spanning an estimated 200,000 light-years in diameter. Between the Milky Way and Andromeda floats a third, smaller spiral galaxy, known as the Triangulum Galaxy, alongside more than 50 dwarf satellite galaxies tethered to the larger systems by mutual gravitational attraction. To conceptualize the scale of the local group, we must adjust our mental map of cosmic distances. While stars within the Milky Way are separated by distances millions of T greater than their physical diameters, galaxies within clusters are located surprisingly close to one another relative to their overall physical dimensions. The 2.5 million light-years separating the Milky Way from Andromeda represents only about 25 the diameter of our galactic disk. If the Milky Way were reduced to the size of a standard dinner plate roughly 30 centimeters across, the Andromeda Galaxy would be a slightly larger plate situated just 7.5 meters away. The space between them is not populated by dense stellar fields, but by the ultra-sparse intergalactic medium, an environment where thermal gas densities drop to fewer than 10 atoms per cubic meter, far colder and emptier than anything found within the galactic disk. Swarming around our galaxy like moths around a streetlight are numerous dwarf satellite systems, including the large and small Magellanic Clouds, the Sagittarius Dwarf Spheroidal Galaxy, and the Ursa Minor Dwarf. The Large Magellanic Cloud, visible from the southern hemisphere, orbits the Milky Way at a distance of roughly 160,000 light-years, spanning 14,000 light-years across and housing roughly 20 billion stars. These satellite galaxies are continuously subjected to immense galactic tide forces as they loop through their orbits. The powerful gravitational well of the Milky Way strips away their outer gas reservoirs and stellar streams, gradually consuming them over cosmic TKLEs in a continuous process of galactic cannibalism. This regional dynamics introduces what astrophysicists refer to as the gravitational island paradox. On large cosmic scales, the overall universe is expanding continuously, with space itself stretching and driving distant galaxies away from one another at ever-increasing speeds. Yet, despite this universal expansion, the Milky Way and the Andromeda Galaxy are currently rushing toward one another at approximately 110 kilometers per second. This local inward movement occurs because the mutual gravitational attraction between the concentrated mass of the local group is powerful enough to locally overcome the background expansion of space. Within this 10 million light-year pocket, gravity reigns supreme, holding the local group together as a bound, coherent system, while the broader universe expands away beyond its borders. In approximately 4.5 billion years, this inward orbital motion will culminate in a titanic cosmic collision. The Milky Way and Andromeda will pass directly through one another, their immense dark matter halos merging first, followed by long gravitational distortion events that will tear giant tidal tails of stars millions of light-years out into space. Because of the vast distances separating individual stars within both galaxies, stellar collisions will remain virtually non-existent during this encounter. Instead, the two spiral disks will undergo a complex gravitational dance over hundreds of millions of years, eventually settling into a single, massive, featureless elliptical galaxy often referred to as Milkdromeda. The intricate spiral structure of our home galaxy will be permanently erased, transformed into a smooth, spherical cloud of aging reddish stars. Analyzing the mass distribution of the local group highlights the overwhelming influence of invisible matter, the combined visible stellar matter of the Milky Way, Andromeda, Triangulum, and all 50 dwarf satellites accounts for less than 15% of the cluster's total mass. The remaining 85% consists of cold dark matter, an unknown, non-baryonic substance that does not emit, absorb, or reflect electromagnetic radiation. This dark matter forms massive spherical halos that enclose each galaxy and extend far out into the intergalactic void, overlapping to form a continuous gravitational substrate. It is the invisible mass of these dark matter halos that provides the gravitational glue necessary to keep the local group intact against the expanding fabric of space-time. When we view the local group within its broader cosmic environment, however, its physical grandeur begins to evaporate. Containing just two major spiral galaxies and a handful of dwarf companions, the local group is classified by cosmologists as a relatively small, sparse galactic group. Massive galaxy clusters elsewhere in the universe, such as the Virgo cluster or the Coma cluster, house thousands of giant galaxies packed into regions only a few larger than the local group. The Virgo cluster alone contains over 1,500 major galaxies and generates a gravitational field so intense that it exerts a measurable pull on every galaxy within 50 million light-years, including our own. The cognitive shift realized at this stage is that the Milky Way is not a solitary island in an empty void, nor is it a central metropolis. It is merely one half of a binary pair residing in a quiet, rural backwater of a much larger cosmic architecture. The 10 million light-year span of the local group, which encompasses every satellite galaxy and every intergalactic gas stream tethered to our home, represents only a microscopic domain when placed alongside the structural webs that bind the universe together. To see where the local group fits within the grand tapestry of space, we must expand our view by another order of magnitude, leaving our local gravitational island behind to map the colossal rivers of matter that flow across superclusters. Furthermore, the gravitational interaction between the Magellanic Clouds and the Milky Way provides a living laboratory for studying galactic tidal stripping. As the large and small Magellanic Clouds complete their periodic passage around our galaxy, a massive stream of neutral hydrogen gas known as the Magellanic Stream has been pulled out of the dwarf systems, forming an arc that wraps across more than 100 degrees of the night sky. This gaseous trail contains an enormous mass of uncondensed hydrogen, which will eventually fall into the Milky Way's galactic disk over the next billion years, triggering a major revival of star formation in our galaxy's outer spiral arms. Moreover, satellite galaxy dynamics reveal subtle challenges to our understanding of dark matter distribution. Precise astrometric mappings conducted by modern space observatories demonstrate that many of the Milky Way's dwarfed satellite galaxies do not orbit in random, isotropic orientations. Instead, they're aligned along a thin, co-rotating planar structure known as the vast structure of satellites. This planar alignment presents an intriguing puzzle for standard cold dark matter computer simulations, which predict that satellite galaxies should be captured from random directions and form a roughly spherical distribution around the main host galaxy. Resolving these satellite dynamics requires sophisticated numerical simulations that model both gravitational dynamics and complex hydrodynamics of intergalactic gas. As dwarf galaxies fall into the local group along cosmic filaments, their gas is subjected to ram pressure, stripping a process where the thin intergalactic plasma pushes against the dwarf galaxy's gas reservoir, blowing it out into deep space. This ram pressure stripping effectively starves the dwarf galaxies of fuel, halting their internal star formation and converting them into passive spheroidal systems. Thus, the local group is not a static collection of galaxies, but an evolving ecosystem where large systems consume smaller ones. Gas is recycled across millions of light years, and gravity slowly shapes a shared destiny across billions of years. Furthermore, numerical gravitational simulations of the local group's orbital trajectory indicate that the Milky Way and Andromeda have experienced multiple close tidal encounters across cosmic history. As the two giants orbit within their shared dark matter envelope, tidal friction gradually extracts orbital energy from their baryonic components, converting orbital momentum into thermal heat within the diffuse intergalactic halo. This orbital decay ensures that their upcoming collision is not a brief flyby, but an inescapable gravitational merger that will permanently reshape the regional structure of our local universe. Additionally, dwarf spheroidal galaxies within the local group serve as pristine laboratories for testing dark matter models. Unlike massive spiral galaxies, where complex baryonic processes such as supernova feedback, stellar winds, and radiation pressure strongly influence mass distribution, dwarf spheroidals are dark matter-dominated systems where baryonic matter accounts for less than 1% of total mass. High-dispersion stellar spectroscopy of individual stars in the fornax and sculptor dwarf galaxies confirms that dark matter halos possess broad, dense cores rather than sharp central cusps, offering crucial observational constraints for cold dark matter and self-interacting dark matter theories. Laniakea supercluster, cosmic flows and gravitational basins, pulling back to an observational scale of 500 million light-years, reveals that the local group is not an isolated cluster, but a minor appendage of an unimaginably larger structure, the Laniakea supercluster, discovered through high-precision velocity mapping of thousands of surrounding galaxies. Laniakea, a Hawaiian name meaning immense heaven, defines the local gravitational watershed of our region of the universe, spanning over 500 million light-years in length and containing the collective mass of more than 100,000 large galaxies. Laniakea represents a structural tier of cosmic organization so immense that light requires 500 million years just to travel from one boundary to the other. To understand the nature of a supercluster, one must abandon the idea of a simple rotating object like a star or a spiral galaxy. Superclusters are not rigid, bound mechanical entities held together by tight central orbits. Instead, they are vast cosmic basins defined by the peculiar velocity flows of galaxies drifting through space. Every galaxy in our region of the cosmos is subject to two distinct velocities: the smooth, uniform outward movement caused by the expansion of the universe, and a local peculiar velocity caused by the gravitational pulls of surrounding mass concentrations. By subtracting the uniform cosmic expansion from the measured motion of thousands of galaxies, astrophysicists revealed a hidden network of cosmic streams, gravitational rivers, along which entire galaxies, including the Milky Way, are actively flowing. At the heart of the Laniakea supercluster lies a mysterious gravitational concentration known as the Great Attractor. Located approximately 220 million light-years from Earth in the direction of the southern constellation Centaurus. The Great Attractor is a massive gravitational anomaly, possessing a mass equivalent to tens of thousands of Milky Ways. It draws the Milky Way, the Andromeda Galaxy, the Virgo Cluster, and thousands of surrounding galaxy groups toward its center at speeds of hundreds of kilometers per second. Our entire galaxy is currently hurtling through the cosmic void toward this distant gravitational basin, carried along a streamline of space-time like a leaf floating down a river. Mapping the boundary of Laniakea requires identifying the cosmic divide where gravitational flow changes direction. Just as rainfall on a mountain ridge flows down into two distinct river basins based on which side of the crest it falls, galaxies in deep space flow toward different gravitational centers based on their position relative to cosmic watershed boundaries. Galaxies on one side of the Laniakea boundary flow inward toward the Great Attractor and the central core of our supercluster, while galaxies just beyond that boundary flow outward toward neighboring superclusters, such as the Perseus-Pisces supercluster or the Shapley concentration. On this scale, the Milky Way's identity shifts entirely. It is no longer a majestic disk of suns, but a single vector in a mathematical velocity field, an infinitesimal dot moving along a cosmic flow line. The sheer volume of space encompassed by Laniakea defies human spatial comprehension. If we return to our conceptual scaling exercise where the entire solar system was compressed to the size of a 1 millimeter coin and the Milky Way spanned 22 kilometers, the Laniakea supercluster on this same scale would stretch across more than 110,000 kilometers. This distance is more than a quarter of the actual physical gap between the Earth and the Moon. Within this vast domain, the 100 billion stars of the Milky Way are reduced to a microscopic speck, indistinguishable from the tens of trillions of other stars swarming within the supercluster's glowing filaments. Furthermore, Laniakea itself is not the ultimate gravitational power in our region of space. Far beyond the Great Attractor, situated roughly 650 million light-years away, lies the Shapley concentration, the most massive collection of galaxy clusters in the local universe. The gravitational pull of the Shapley concentration is so immense that it acts as a secondary attraction point, pulling the Great Attractor and the entire Laniakea supercluster toward it across the intergalactic expanse. We are witnessing a nested hierarchy of cosmic motion, the Earth orbiting the Sun orbiting the center of the Milky Way falling toward the Andromeda Galaxy, the local group flowing toward the Great Attractor, and the entire Laniakea basin being dragged toward the Shapley concentration. This complex cosmic flow highlights a fundamental principle of modern astrophysics. Mass tells space how to curve, and curved space tells matter how to move. The distribution of matter across supergalactic scales creates deep potential wells in the fabric of space-time, guiding the drift of galaxies across billions of years. Yet, because these superclusters are so sprawling and diffuse, their outer regions are not fully bound by gravity. The continuous acceleration caused by dark energy is actively pulling the outer fringes of Laniakea apart, ensuring that many of its constituent galaxy groups will eventually be severed from one another before they can ever assemble into a single merged structure. The cognitive shift occurring at the supercluster scale is the complete dissipation of galactic individuality. Within the boundary of Laniakea, individual galaxies lose their status as dominant astronomical objects and become mere tracer particles, like dust motes suspended in a sunbeam. The Milky Way, with all its deep history, its billions of solar systems, and its complex spiral arms, is revealed to be nothing more than an unremarkable component of a vast fluid-like flow. To see the true pattern formed by these superclusters, we must pull back even further, stepping out to the megaparsec scale where the grandest architecture of the universe finally emerges from the dark. Consider how astrophysicists map these cosmic flows using cosmic distance ladder techniques. Measuring the precise distances to tens of thousands of galaxies requires combining multiple independent indicators such as Cepheid variable stars, type Ursa supernovae, and the Tully-Fisher relation, which connects a spiral galaxy's rotational velocity to its total intrinsic luminosity. By measuring a galaxy's redshift and comparing it against its independent distance measurement, astronomers can isolate its peculiar velocity, the component of its motion driven solely by local gravitational pulls rather than the overall expansion of space. When these peculiar velocity vectors are plotted across a three-dimensional volume of space, the intricate streaming patterns of Laniakea emerge. Entire strands of galaxies, stretching across hundreds of millions of light-years, are seen sliding smoothly along gravitational potential gradients toward the Great Attractor. This flow field resembles a vast cosmic web of tributaries feeding into a central bay, illustrating how gravity organizes matter across scales that span a significant fraction of the observable cosmos. However, observing the core of the Great Attractor presents a unique observational challenge known as the zone of avoidance. Located in the direction of the constellation Centaurus, the Great Attractor sits directly behind the dusty plane of our own Milky Way disk. The dense interstellar dust and millions of stars in our galactic plane absorb and scatter optical light from distant galaxies, effectively obscuring roughly 20% of the extragalactic sky. For decades, this optical barrier masked the true nature of the Great Attractor, forcing astronomers to deploy infrared, radio, and X-ray space observatories to peer through the galactic dust and reveal the massive galaxy clusters hidden behind our own home disk. This observational barrier highlights a poignant cosmic irony. The very galaxy we inhabit, the dense stellar disk of the Milky Way, acts as a blind spot that hides some of the largest structures in the universe from our view. To map the true scope of Laniakea and the surrounding superclusters, human science had to develop multi-wavelength astronomy, using invisible frequencies of light to bypass our local galactic dust and illuminate the vast cosmic architecture beyond. Investigating the internal kinematics of the Laniakea supercluster illuminates how massive gravitational structures influence cosmic velocity fields. The velocity field within Laniakea is mapped using the cosmic distance ladder, where peculiar velocities are isolated by subtracting Hubble flow expansion from measured galaxy redshifts. This reveals that galaxies throughout our supercluster are accelerating along well-defined streamlines toward the Great Attractor, creating a massive cosmic flow that spans over 500 million light-years. Moreover, the boundary of Laniakea represents an active watershed threshold in observational cosmology. Galaxies situated near the outer fringe of Laniakea experience competing gravitational forces between the Great Attractor and the adjacent Perseus-Pisces supercluster. As space-time continues to expand under dark energy, these boundary regions will eventually experience gravitational shearing, tearing Laniakea apart into isolated cluster subunits before complete structural collapse can ever take place across the entire supercluster volume. Cosmic web filaments, sheet horizons, and supervoid mechanics. When the observational perspective is widened to encompass billions of light-years, the distribution of matter in the universe resolves into a stunning, continuous geometric structure known as the cosmic web. Matter does not scatter randomly through the abyss, nor does it form isolated uniform spheres. Instead, driven by the subtle seeds of primordial quantum fluctuations amplified over 13.8 billion years of gravitational collapse. The universe has organized itself into a sprawling network of interconnected filaments, broad planar sheets, dense structural nodes, and vast, empty voids. This cosmic web represents the absolute largest physical pattern formed by matter in space-time. The structural nodes of the cosmic web are anchored by massive superclusters like Laniakea and the Shapley concentration, where thousands of galaxies converge at high-density intersections. Stretching between these dense nodes are long, luminous filaments composed of dark matter, intergalactic gas, and millions of aligned galaxies. These filaments act as the structural highways of the cosmos, channeling fresh streams of hydrogen gas and small galaxy groups into the growing supercluster nodes. Between these long filaments stretch vast planar sheets of galaxies, forming thin walls that enclose immense hollow caverns of absolute nothingness known as supervoids. Supervoids are perhaps the most astonishing feature of the cosmic web. These are colossal spherical regions of space that contain virtually no galaxies, no stars, and almost no baryonic matter whatsoever, spanning anywhere from 50 million to over 300 million light-years in diameter. Supervoids represent the true dominant volume of the universe. One of the most famous of these empty structures is the Butter's Void, a terrifying expanse of space roughly 330 million light-years across. Located in the direction of the constellation Butter's, this vast volume of space is so empty that if the Milky Way had been located in its center, human astronomers would not have discovered other galaxies until the advent of advanced electronic telescopes in the mid-20th century. We would have believed our galaxy was the sole object in existence. Recent cosmological surveys suggest that our own Milky Way may reside near the edge of an exceptionally large low-density region known as the KBC Void. Named after astronomers Keenan, Barger, and Cowie, spanning nearly 2 billion light-years across, the KBC Void is a massive spherical underdensity in the distribution of local galaxies. If confirmed, this indicates that the entire Laniakea supercluster, along with several neighboring superclusters, resides inside a broad cosmic depression where the average density of matter is roughly 20 to 30% lower than the universal mean. This cosmic location explains why local measurements of the universe's expansion rate somewhat differ from distant cosmic microwave background calculations, as matter inside the underdense void is pulled outward toward the denser walls surrounding it. The mechanics governing supervoid formation are rooted in gravitational competition. In the early universe, regions of space that were slightly denser than average exerted a stronger gravitational pull, gradually drawing matter away from adjacent regions that were slightly less dense. Over billions of years, this process ran away exponentially. Dense regions grew denser, collapsing into the tight filaments and nodes of the cosmic web, while underdense regions were stripped of their matter, expanding into massive hollow voids. The voids are not merely empty space, they are active thermodynamic systems where dark energy exerts an unchecked outward pressure, driving matter away from their centers and flattening surrounding galaxies against the cosmic walls. On this megaparsec scale, matter becomes an extreme exception in a cosmos dominated by void space. More than 80% of the volume of the observable universe consists of hollow supervoids, while the entirety of luminous matter, every star, planet, gas cloud, and galaxy is confined to the thin, delicate filaments that wrap around these empty caverns. The Milky Way, which once seemed like an imposing universe unto itself, is now revealed to be a tiny dust grain clinging to a single strand of cosmic spiderweb, suspended over an infinite gulf of absolute empty space. The scale comparison at this stage borders on the absurd. If we reduce the entire observable cosmic web down to the size of a human sphere of vision, roughly 10 meters across, a single galaxy like the Milky Way would be far smaller than a single biological cell. It would be an invisible speck floating along a thread of light barely a few micrometers thick. The hundreds of billions of stars within our galaxy, along with every planet that has ever formed around them, are condensed into a physical volume so small that it escapes human vision entirely. The universe is not a collection of stars with space between them. It is an immense structure of empty space bounded by micro-thin threads of matter. The cognitive shift enforced by the cosmic web is the realization that the primary character of the universe is emptiness, not structure. Human intuition naturally focuses on luminous object stars, nebulae, bright galactic disks because they emit the light that reaches our eyes. But scientifically, these bright structures are merely rare surface anomalies resting atop a vast ocean of empty space and dark matter. The Milky Way exists only because it occupies a rare gravitational ripple in a universe designed predominantly for emptiness. To truly measure our galaxy against reality, we must look beyond even these vast filaments and measure the ultimate boundary of light itself, the edge of the observable universe. Deep examination of cosmic web mechanics reveals the crucial role of the warm-hot intergalactic medium, or WHIM. Cosmologists long faced the missing baryon problem when counting all visible stars, gas clouds, and galaxies in the universe. More than half of the normal baryonic matter predicted by Big Bang nucleosynthesis appeared to be missing. High-resolution X-ray spectroscopy revealed that this missing matter resides within the vast filaments of the cosmic web, taking the form of a diffuse, highly ionized gas at temperatures between 100,000 and 10 million Kelvin. This warm-hot plasma traces the dark matter filaments, acting as a cosmic circulatory system that feeds fresh gas into galaxies while interconnecting the structural nodes of the universe. Furthermore, computer simulations of cosmic structure formation such as the Illustris and Millennium simulations demonstrate how dark matter acts as the primary scaffolding for the cosmic web. Because dark matter interacts only through gravity, it began collapsing into filaments long before normal baryonic matter could cool and collapse. Normal gas then fell into these pre-existing dark matter gravitational wells, cooling and condensing at high-density nodes to ignite the first stars and seed early galaxies. Thus, the glowing strands of galaxies we see across billions of light-years are merely luminous paint sprayed onto an invisible, massive skeleton of dark matter that defines the cosmic architecture. Investigating the internal hydrodynamics of cosmic supervoids exposes how dark energy dominates regional cosmic expansion. While galaxy clusters and filaments are held together by mutual gravity, supervoids experience an outward acceleration driven by negative pressure. Gas and rare dwarf galaxies within voids are pushed outward toward the dense boundary walls, leaving the void centers as ultra-pure vacuum regions containing virtually zero heavy elements or dark matter structures. Furthermore, supervoids act as powerful gravitational lenses through the integrated Sachs-Wolf ISW effect. As cosmic microwave background photons travel through an expanding supervoid, they enter the void's gravitational potential well and lose energy as space expands while they cross it. When those photons emerge from the void on the far side, the potential well is stretched and flattened due to dark energy acceleration. Consequently, photons emerge from supervoids with slightly less energy, creating cold spots in the cosmic microwave background sky that allow cosmologists to measure the repulsive strength of dark energy across cosmic time. Examining the topology of the cosmic web using persistent homology and Betty numbers provides a rigorous mathematical description of cosmic filaments and supervoids. In topological data analysis, galaxies are treated as spatial point processors, where zeroth-order Betty numbers, zeroth-order topology measure connected galaxy clusters. First-order Betty numbers, first-order topological loops identify cosmic loops and filamentary rings, and second-order Betty numbers, second-order void volumes quantify enclosed empty supervoid volumes. This mathematical framework demonstrates that the cosmic web is topologically complex, featuring a continuous sponge-like architecture where high-density filaments form structural walls around cavernous supervoids. Computer simulations reveal that as the universe expands, second-order Betty numbers increase, reflecting the continuous growth of supervoid volumes as dark energy drives matter out of underdense regions into surrounding cosmic filaments. Observable universe, light horizon expansion and particle horizons. Beyond the vast geometric web of filaments and voids lies the fundamental observational boundary of physical reality, the edge of the observable universe. The observable universe is defined as the spherical volume of space from which light emitted since the beginning of cosmic time has had sufficient time to reach an observer on Earth. Because the universe has a finite age of approximately 13.8 billion years, and because light travels at a finite speed, we cannot see an infinite distance into space. There is a cosmic horizon beyond which no information, no light, and no gravitational influence can ever reach us, regardless of how powerful our telescopes become. A common misconception regarding the size of the observable universe stems from a simple calculation if the universe is 13.8 billion years old. One might assume that the observable horizon extends 13.8 billion light-years in every direction, creating a sphere 27.6 billion light-years across. However, this simple calculation assumes that space itself is static and unyielding. In reality, the fabric of space-time has been expanding continuously throughout the past 13.8 billion years. The distant regions of space that emitted the cosmic microwave background light we detect today were indeed only about 42 million light-years away from our location when that light was first emitted. But during the 13.8 billion years that light spent traveling toward us, the space between those distant regions and Earth expanded dramatically. When astrophysicists account for the continuous expansion of space using general relativity, the present physical distance to the edge of the observable universe, known as the comoving distance, stretches to approximately 46.5 billion light-years in every direction. This defines the particle horizon, a massive spherical volume spanning roughly 93 billion light-years in total diameter. This 93 billion light-year sphere represents the absolute total of everything humanity can physically see, measure, or interact with in the cosmos. It contains an estimated 2 trillion individual galaxies, each housing hundreds of billions of stars, resulting in a total stellar population exceeding 200 sextillion suns. To compare the Milky Way against this ultimate observational boundary, we must perform a mathematical ratio calculation. The diameter of the Milky Way's visible disk is 100,000 light-years, 100,000 light-years. The diameter of the observable universe is 93 billion light-years. Dividing the diameter of our galaxy by the diameter of the observable sphere yields a ratio of roughly 1 to 930,000. While this linear ratio seems vast, spatial volume scales with the cube of the radius, where volume scales with the cube of the radius. When we calculate the volumetric ratio, the result becomes staggering. The volume of the observable universe is roughly 3.5 T10 to the 17th power T larger than the physical volume of the Milky Way disk. If we represent the entire 93 billion light-year observable universe as a sphere the size of planet Earth, the Milky Way galaxy on this scale would not be a continent, a city, or even a house. Our entire home galaxy, with all its 400 billion stars and its sprawling spiral arms, would be a tiny grain of sand less than a millimeter in diameter, buried somewhere within the Earth's vast crust. Every human being who has ever lived, every historical event, every astronomical observation, and every planetary body ever discovered is confined to an atom-sized speck, located inside that single grain of sand. Furthermore, the particle horizon is not a fixed physical wall in space. It is a dynamic observational boundary centered on the specific location of the observer. An observer situated in a distant galaxy 40 billion light-years away would stand at the center of their own unique 93 billion light-year observable sphere. Their horizon would encompass regions of space that are completely invisible to us, while excluding vast portions of the universe that we can see. The observable universe is not a definitive containment vessel for the cosmos. It is merely a personal optical bubble dictated by the finite speed of light and our specific coordinates in space-time. The cosmic microwave background radiation marks the absolute physical wall of this optical bubble, emitted roughly 380,000 years after the Big Bang, when the expanding universe cooled sufficiently for neutral hydrogen atoms to form and release trapped photons. The cosmic microwave background forms an opaque sphere of thermal radiation surrounding our observable bubble. We cannot look past this glowing wall using optical or infrared telescopes, because prior to that moment, the universe was a dense, opaque plasma of free electrons and protons that scattered light like a thick fog. The cosmic microwave background is the ultimate background image of our observable sky, representing the infant universe frozen in light. The cognitive shift demanded by the particle horizon is the realization of our absolute spatial isolation. The 93 billion light-year sphere of the observable universe is not just a large room, it is a hard physical limit on human knowledge. Everything we can ever know about reality through electromagnetic radiation, gravitational waves, or particle detection is strictly confined within this bubble. Yet, the physical laws of nature dictate that space does not simply stop at the edge of our observable sphere. The fabric of space-time continues smoothly past our horizon into regions we can never see. To understand what lies past this ultimate optical wall, we must examine the relativistic physics of expanding space and the concept of the Hubble volume. Analyzing the mathematics of co-moving coordinates reveals how expanding space alters our perception of distant astronomical events. In an expanding Friedmann-Lemaitre-Robertson Walker FLRW metric, the physical distance between two stationary observers is related to their scale factor, cosmic scale factor, by where physical distance equals the scale factor multiplied by comoving distance, where comoving distance is the constant comoving coordinate distance. As light travels across expanding space, its wavelength is stretched proportionally to the scale factor, a phenomenon known as cosmological redshift, where redshift is defined by the expansion factor. The oldest light we observe today from the cosmic microwave background has been stretched by a redshift factor of the density variation is less than 0.004 p prox. 1100. The density variation is less than 0.004, transforming high-energy ultraviolet radiation emitted by infant plasma into cold, invisible microwave photons that wash over Earth from all directions. Furthermore, the concept of the particle horizon highlights the fundamental temporal nature of deep space astronomy. Looking far away in distance inherently means looking back in time. When we photograph a galaxy 40 billion light-years away in comoving distance, we do not see that galaxy as it exists today. We see it as it existed over 13 billion years ago, when it was a young, turbulent proto-galaxy assembling its first generation of stars. Thus, our 93 billion light-year observable sphere is simultaneously a map of spatial volume and a temporal museum of cosmic history, recording the evolution of matter from the hot primordial plasma of the Big Bang to the complex galactic networks of the present day. Deep analysis of the comoving distance calculation highlights the difference between physical distance and light travel distance in an expanding FLRW metric. The comoving distance is defined as where comoving distance is integrated across cosmic expansion history, where the Hubble expansion rate is the Hubble parameter as a function of redshift. During early cosmic epochs, when matter dominated the energy density of space, the Hubble expansion rate evolved according to matter density scaling the cube of redshift scaling. As dark energy became dominant at redshift 0.4, the rate of cosmic expansion transitioned from deceleration to acceleration. This acceleration pushed the current particle horizon out to 46.5 billion light-years, creating an expansive spherical boundary. If space expansion were unaccelerated, the particle horizon would be significantly smaller. Furthermore, because light from the particle horizon was emitted when the universe was only 380,000 years old, those primordial photons have experienced an extreme cosmic stretch, transforming from high-energy ionizing ultraviolet light into a cold, homogeneous microwave radiation field that permeates every cubic centimeter of deep space today. Probing the thermodynamics of the particle horizon requires examining the redshift evolution of the cosmic background radiation temperature. In FLRW metric cosmology, the temperature of the cosmic microwave background scales inversely with the scale factor, where cosmic temperature decreases proportionally with space expansion. At the moment of recombination, the temperature of the primordial plasma was roughly 3000 Kelvin, vibrant enough to ionize hydrogen atoms and trap photons through Thomson scattering. As space expanded by a factor of 1100 over 13.8 billion years, those primordial photons were stretched to microwave frequencies, cooling the background temperature to 2.725 Kelvin. Today, these ancient photons form an isotropic background field containing roughly 411 photons per cubic centimeter of space, carrying an unerased physical record of the infant universe from the outer particle horizon directly into our terrestrial detectors. Hubble volume and the relativistic speed of distant space. The expansion of the universe leads directly to one of the most counterintuitive concepts in modern physics, the Hubble volume and superluminal spatial expansion. According to Hubble's law, the recessional velocity of a distant galaxy is directly proportional to its distance from the observer. The farther away a galaxy is located, the faster the space between us and that galaxy is expanding. At moderate distances, this expansion causes the light from distant galaxies to shift toward the red end of the electromagnetic spectrum. However, because space expansion is cumulative over distance, there inevitably exists a critical distance where the recessional velocity of space equals the speed of light itself. This critical boundary is known as the Hubble radius, and the spherical volume of space enclosed by it is called the Hubble volume. The Hubble radius is calculated by dividing the speed of light by the Hubble constant, where the Hubble radius equals the speed of light divided by the Hubble constant, yielding a radius of approximately 14.4 billion light-years from Earth. Inside the Hubble volume, space is expanding at speeds slower than light, allowing light emitted by distant galaxies to travel toward us and make progress across space. Outside the Hubble volume, however, the fabric of space is expanding away from us at speeds that exceed the speed of light. It is vital to understand that superluminal spatial expansion does not violate Einstein's theory of special relativity. Special relativity dictates that no physical object, particle, or signal can move through space faster than the speed of light. However, general relativity imposes no such speed limit on the expansion of space itself. Space is not a physical material moving through a medium, it is the metric fabric in which matter resides. When space expands, it does not accelerate matter through space. Rather, it creates new space between points, carrying galaxies along with it. Therefore, galaxies situated beyond the Hubble radius are not moving through space at superluminal speeds. Space itself is stretching between us and them faster than light can cross the gap. This relativistic phenomenon creates a profound disconnect between the Hubble volume and the observable universe. The Hubble radius extends out to roughly 14.4 billion light-years, while the observable universe extends out to 46.5 billion light-years. This means that a massive region of space spanning between 14.4 and 46.5 billion light-years from Earth is currently expanding away from us at superluminal speeds. We can still see many of the galaxies located in this superluminal region today because the light they emitted billions of years ago was released when those galaxies were much closer to us. Inside our historical Hubble volume, that ancient light managed to cross the expanding gap and reach our modern telescopes. However, any light emitted by those superluminal galaxies today right at this very second can never reach Earth. The space between us and those galaxies is stretching faster than the emitted photons can travel through space. Those photons will spend eternity fighting against an expanding spatial current that moves faster than their travel speed, like a swimmer trying to swim upstream against a waterfall that flows faster than their maximum stroke speed. Consequently, those distant galaxies have already crossed a causal threshold. We are looking at their ancient past, but we are permanently severed from their present and their future. When we evaluate the Milky Way within the context of the Hubble volume, the shrinking nature of our sphere of influence becomes terrifyingly clear. The total volume of space from which we can actively receive new causal signals is continuously shrinking relative to the expanding cosmos. Out of the 2 trillion galaxies currently visible within our 93 billion light-year observable sphere, an estimated 97% have already crossed the Hubble horizon. They are already expanding away from us faster than light. Only 3% of the galaxies we see in the night sky today are still causally accessible to us in real time. The remaining 97% are cosmic ghosts, objects whose past light continues to wash over Earth, but whose current existence is forever lost behind a relativistic spatial barrier. The scale reduction comparison at this stage reveals the absolute temporal fragility of our cosmic position. If the entire Hubble volume was scaled down to the size of a single human room, the Milky Way would be an invisible atomic particle floating in the air. The vast majority of the room around that particle would consist of space that is actively rushing away faster than light, severing all potential future communication. The home galaxy we inhabit is not just a small particle in space, it is a particle locked inside a rapidly closing relativistic cage. The cognitive shift imposed by the Hubble volume is the distinction between optical visibility and physical contact. Seeing an object in space does not mean we share a physical future with it. The overwhelming majority of the universe we can photograph with advanced space telescopes is already physically gone from our future universe, receding into the darkness beyond the speed of light. The Milky Way is being progressively isolated, left behind in a local pocket of slow expansion, while the vast ocean of external space expands out of reach. To determine how much larger the total universe is beyond even these expanding horizons, we must turn to the cosmic background radiation and the geometric measurement of spatial curvature. Evaluating the thermodynamics of expanding horizons requires examining the mathematical behavior of the cosmological horizon, where the event horizon is defined by the integrated speed of light across time. As the scale factor, cosmic scale factor, accelerates under dark energy dominance, this integral converges to a finite value, establishing a fixed physical distance beyond which no future light emission can ever reach an observer. This creates a cosmological event horizon that behaves mathematically like an inverted black hole horizon. Instead of trapping light inside a gravitational well, it traps light outside our observational sphere, permanently preventing distant signals from reaching our local region of space. Furthermore, this continuous causal disconnection alters our long-term understanding of cosmic structure. As distant galaxies cross the cosmological event horizon, their light becomes increasingly redshifted and attenuated, fading exponentially in intensity. Over hundreds of billions of years, the visible sky will empty as galaxy after galaxy disappears behind this relativistic barrier. The Hubble volume serves as a fundamental physical boundary that separates the causally connected universe from the unreachable expanse beyond, highlighting how the Milky Way is slowly being marooned in an ever-expanding cosmic sea. Examining the kinematics of superluminal expansion clarifies how the Hubble volume governs causal contact in an expanding universe. The recessional velocity, the density variation, is less than 0.004 v-rec. The density variation is less than 0.004 of a galaxy located at physical distance. The density variation is less than 0.004. The density variation is less than 0.004 is given by Hubble's law, where recessional velocity equals the Hubble constant t distance. setting where recessional velocity reaches the speed of light defines the Hubble radius, where the Hubble radius equals the speed of light divided by the Hubble constant. Beyond this distance, the rate at which new space is created between 2 points exceeds 300,000 kilometers per second. This implies that while we can observe light emitted by distant galaxies when they were inside our past light cone, those galaxies have now moved beyond the Hubble radius in present time. Any signal, photon, or gravitational wave dispatched by those galaxies today can never reach Earth. They have passed behind an event horizon relative to our current frame of reference. The universe is actively splitting into isolated causal pockets, ensuring that 97% of the galaxies visible in our current night sky are already physically disconnected from our future timeline. Evaluating the relativistic metric of the Hubble sphere clarifies the physical distinction between particle horizons and event horizons. In an accelerating de Sitter universe dominated by a cosmological constant, the Hubble radius, where the Hubble radius equals the speed of light divided by the Hubble constant, asymptotes toward a constant physical value. This creates a stationary cosmic event horizon that encloses a finite physical volume from which future emitted light can ever reach our location. Consequently, while our current particle horizon expands as light from distant regions continues to arrive, the comoving volume of causally accessible space is shrinking exponentially. Galaxies currently located near the edge of our observable sphere are crossing the cosmological event horizon, receding at superluminal speeds relative to Earth. Within several Hubble T, all extragalactic objects outside our gravitationally bound local group will fade beyond detection, leaving our home galaxy isolated in an expanding void. Furthermore, the expansion dynamics within the Hubble volume highlight the cosmic event horizon's role as an asymmetric thermodynamic barrier. While Hawking radiation occurs at the event horizon of a black hole, cosmic event horizons in de Sitter space similarly emit a tiny flux of thermal radiation known as Gibbons-Hawking radiation. For our accelerating universe, this horizon temperature is exceptionally tiny. Roughly, the density variation is less than 0.00. Cosmic scale's density variation is less than 0.004. Kelvin confirming that while the Hubble volume isolates our galaxy causally, its quantum radiation is far too faint to affect local physical processes within Milky. Background radiation and the geometry of spatial flatness. To probe the ultimate extent of the universe beyond the observable particle horizon, cosmologists rely on the geometry of spacetime itself. In general relativity, the overall geometric curvature of the universe is determined by its average energy density, represented by the cosmological density parameter omega omega. If omega is greater than 1 omega is greater than 1, the universe possesses positive spatial curvature, forming a closed, finite, four-dimensional hypersphere like the surface of a globe. If omega is less than 1, omega is less than 1. Space possesses negative spatial curvature, forming an open, infinite hyperbolic saddle shape. If omega is exactly equal to 1, omega is equal to 1, space is Euclidean and perfectly flat, stretching infinitely in every direction without ever curving back on itself. Measuring this cosmic curvature with extreme precision is accomplished by analyzing the microscopic temperature fluctuations in the cosmic microwave background radiation, emitted when the universe was just 380,000 years old. The cosmic microwave background contains subtle hot and cold spots produced by acoustic sound waves rippling through the early plasma. The physical size of these acoustic hotspots can be calculated with extreme mathematical precision using known thermodynamic and fluid mechanics principles. These sound waves act as a cosmic standard ruler imprinted on the distant horizon of the universe. By measuring the angular size of these acoustic hotspots as seen from Earth, astronomers can determine how light rays have traveled across space-time over the past 13.8 billion years. If the universe possessed positive spatial curvature, light rays from opposite edges of a hotspot would bend inward toward one another, causing the spot to appear magnified and larger than its true physical angle on the sky. If the universe possessed negative spatial curvature, light rays would curve outward, causing the hot spot to appear smaller and distorted. Precision satellite observatories, most notably NASA's Wilkinson Microwave Anisotropy probe, BMAP, and the European Space Agency's Planck Space Telescope, have measured these acoustic signatures across the entire sky with breathtaking accuracy. The results returned by the Planck satellite confirmed that the density parameter of the universe is equal to 1 within an extraordinary margin of error of less than 0.4% omega is equal to 1.000 plus or minus 0.004. The geometry of our universe, at least across the entire extent of our observable bubble, is exceptionally, remarkably flat. This measurement of spatial flatness has profound mathematical implications for the scale of the unobservable universe beyond our horizon. Just as an observer standing on Earth cannot see the full curvature of the planet because their horizon is too small, we cannot detect any spatial curvature in the universe because our 93 billion light-year observable sphere is too small relative to the global geometry of space. If space was slightly curved into a massive closed sphere, the measured 0.4% margin of error establishes a strict mathematical lower bound on its total size. Calculations based on Planck's curvature limits dictate that if the universe is a closed sphere, the total unobservable volume of space must be at least 250 times larger than our 93 billion light-year observable universe. That means there are at least 250 additional 93 billion light-year spheres packed outside our visible horizon, containing trillions of additional galaxies that we can never see. Furthermore, if the density parameter is precisely equal to 1 as theoretical models of cosmic inflation strongly predict, then the spatial curvature of the universe is 0, and the total physical universe is mathematically infinite. Comparing the Milky Way to an unobservable universe that is at least 250 times larger than our observable bubble pushes spatial ratios past the limits of conventional notation. If our observable sphere contains 2 trillion galaxies, the total physical universe contains at least 500 trillion large galaxies. On this scale, the volumetric fraction represented by the Milky Way drops to less than 1 part in 100 sextillion. 1 part in 100 sextillion. A home galaxy becomes a fraction so microscopic that it approaches mathematical zero. If space is indeed geometrically flat and infinite, the scale comparison breaks down completely. In a universe of infinite spatial volume, the Milky Way is not a small percentage of the cosmos. It is an infinitesimal fraction, a finite quantity divided by infinity, which equals 0. An infinite universe contains an infinite number of galaxies, an infinite number of stars, and an infinite number of physical matter configurations. In an infinite flat universe, every structure that has a non-zero probability of existing must exist an infinite number of TC across the vast spatial expanse. The cognitive shift enforced by spatial flatness is the realization that our observable bubble is not a representative sample of total physical reality. It is merely an infinitesimal patch of a flat geometric canvas that extends far beyond our optical reach. The Milky Way is not sitting near the center or the edge of anything. It is a microscopic dust grain resting on an infinite tabletop. To understand how such an immense, flat space was created, we must step back to the very first fraction of a second after the origin of time and examine the mechanics of cosmic inflation. Analyzing the power spectrum of the cosmic microwave background provides deeper insights into these acoustic oscillations. The angular power spectrum displays a series of distinct multipole peaks, where the first peak corresponds to the fundamental acoustic tone of the primordial plasma, the maximum compression of sound waves entering the horizon at recombination. The precise location of this first peak at multipole, the density variation is less than 0.004 piprox. 220. The density variation is less than 0.004 confirms with extreme statistical confidence that parallel light rays travel along straight lines across billions of light years, adhering perfectly to Euclidean geometry. Furthermore, the flatness of space poses what cosmologists historically termed the flatness problem. In standard Big Bang cosmology without inflation, any slight deviation of omega from unity in the early universe would be rapidly amplified by gravity over time. For omega to be measured as close to 1 today, omega at 1 second after the Big Bang must have been equal to 1 to within 1 part in the density variation is less than 0.00. Cosmic scales, density variation is less than 0.004. This extraordinary fine-tuning of primordial density strongly implies the action of a dynamic flattening mechanism in the early universe, establishing the necessary theoretical bridge to cosmic inflation theory. Investigating the statistical isotropy and spatial Gaussianity of the cosmic microwave background confirms the geometric precision of spatial flatness. Precision power spectrum measurements across multipoles from the density variation is less than 0.004. The density variation is less than 0.004 out. To the density variation is less than 0.004. 2500. The density variation is less than 0.004. Show that temperature fluctuations conform strictly to Gaussian random fields seeded by primordial quantum fluctuations. The absence of non-Gaussian anomalies across large angular scales confirms that space-time curvature is exceptionally zero across the entire observable volume. Furthermore, the mathematical relation between density parameter omega and spatial curvature, the density variation is less than 0.004. The density variation is less than 0.004 in the Friedmann equation, reveals why flatness dictates an immense physical universe. Because the scale factor, cosmic scale factor, has expanded by more than 60 orders of magnitude since the Big Bang. Any initial non-zero curvature, the density variation is less than 0.004, the density variation is less than 0.004 would have been flattened out completely during inflation. If omega is identically equal to 1, the universe possesses zero spatial curvature, representing a flat Euclidean 3 space that extends without bound across infinite dimensions. Analyzing the polarization modes of the cosmic microwave background offers direct empirical testing of spatial flatness and primordial gravitational waves. The CMB radiation exhibits subtle linear polarization generated by Thomson scattering off free electrons during recombination, decomposed into curl-free E modes and divergence-free B modes. Precision measurements of E-mode polarization spectrum by ground-based observatories confirm Euclidean geometric propagation across cosmological distances. Furthermore, primordial B-mode polarization patterns, if detected, would provide an direct signature of tensormetric perturbations generated during cosmic inflation. The amplitude of these tensor modes, parameterized by the tensor-to-scalar ratio Comoving distance, directly measures the energy scale of inflation, confirming that space was stretched to geometric flatness at energy scales near the grand unified theory gut energy limit. Additionally, spatial flatness provides essential initial conditions for cosmic inflation models. In inflationary cosmology, the inflaton field must roll down a sufficiently flat potential. The density variation is less than 0.004 V. The density variation is less than 0.004, satisfying the slow roll conditions. The density variation is less than 0.004. MDPL22 VV2. The density variation is less than 0.004, and the density variation is less than 0.004. MPEL2V. The density variation is less than 0.004. These slow-roll dynamics guarantee that inflation persists long enough to expand spatial volume by at least 60 E-folds, driving spatial curvature to zero and establishing the homogeneous Euclidean background recorded by CMB observatories. Cosmology and the infinite spatial topology. The extraordinary flatness and extreme spatial scale of the universe are explained by the theory of cosmic inflation, developed by physicists Alan Guth, Andrei Linde, and Alexei Starobinsky in the early 1980s. Cosmic inflation posits that during the first minute fraction of a second following the Big Bang between the density variation is less than 0.00 cosmic scales, density variation is less than 0.004, and the density variation is less than 0.00. Cosmic scales density variation is less than 0.004 seconds. After the initial singularity, the universe underwent a phased transition that drove an exponential expansion of space-time. Driven by a high-energy scalar field known as the inflaton, space expanded by a mathematical factor of at least the density variation is less than 0.00 cosmic scales. Density variation is less than 0.004 in an infinitesimal fraction of a second, expanding far faster than the speed of light. This hyperfast expansion took a tiny, subatomic region of space billions of to smaller than a single proton and stretched it out into a vast, smooth, geometrically flat cosmos. Inflation acted like an immense iron smoothing out a wrinkled bedsheet. Any initial spatial curvature, anisotropy, or irregularity that existed prior to inflation was stretched out so violently that local space became completely flat, explaining why modern satellites measure a density parameter of precisely 1. When inflation ended, the energy of the inflaton field decayed into a hot, dense plasma of particles, initiating the standard Big Bang expansion that continues today. However, the physics of cosmic inflation introduces a stunning cosmological consequence known as eternal inflation. Because inflation is driven by quantum scalar fields, quantum fluctuations naturally occur within the inflating space. In most regions of space, these quantum fluctuations cause inflation to end, converting scalar field energy into matter and creating localized bubble universes or pocket domains like our own. But in other adjacent regions, quantum fluctuations keep the inflaton field at a high energy level, causing space in those regions to continue inflating exponentially forever. In eternal inflation models, the overall multiverse is expanding at an exponential rate that far outpaces the decay rate of individual bubble domains. As a result, inflation never stops globally. It continuously generates an infinite number of distinct pocket universes, each separated from one another by vast gulfs of exponentially inflating space. Our entire 93 billion light-year observable universe, along with the vast unobservable flat space surrounding it, is merely one single pocket universe embedded within an ever-expanding, infinite inflationary multiverse. Within our own specific bubble universe, cosmic inflation stretched space to such a degree that its physical volume may be effectively infinite, or at least vastly larger than the minimum limit set by curvature measurements. Theoretical estimates by cosmologists Andrei Linde and Alexander Vilenkin suggest that the physical scale of our single post-inflationary bubble domain could be at least the density variation is less than 0.00 cosmic scales. Density variation is less than 0.004 meters across a number so vast that it cannot be written out in standard decimal form, as it contains more zeros than there are subatomic particles in the entire observable universe. On this inflationary scale, comparing the Milky Way to the post-inflationary spatial expanse requires dealing with double exponential numbers. The 100,000 light-year span of our galaxy becomes utterly meaningless when placed alongside a spatial domain spanning the density variation is less than 0.00 cosmic scales. Density variation is less than 0.004 meters. The Milky Way is not a grain of sand on an Earth-sized sphere. It is a single quantum particle suspended inside a volume of space that defies all mathematical expression. Furthermore, if eternal inflation is correct, the spatial topology of reality expands into a multiverse where even physical constants might vary between individual bubble domains. In adjacent pocket universes, the scalar fields may have decayed differently, resulting in different values for the speed of light, the mass of the electron, or the strength of the strong nuclear force. Our home galaxy, built from stable baryonic matter and governed by precise physical constants, exists only because our specific bubble universe decayed into a low-energy state that permitted stable chemistry, stars, and galaxies to form. The cognitive shift demanded by inflationary cosmology is the absolute dethroning of our universe as a unique physical structure. The Milky Way is no longer just a small galaxy in a large universe. It is a microscopic feature within a single local bubble domain suspended inside an eternal, infinite multiverse that is constantly generating new universes for all eternity. Our home system is a fragile, temporary arrangement of matter riding atop a quantum foam that spans infinity. To understand what will happen to our tiny home galaxy over deep time as space continues to stretch, we must examine the ultimate fate of spatial contact, the cosmic horizon crisis. Examining the quantum mechanical dynamics of the inflaton field reveals how microscopic fluctuations dictate macroscopic cosmic structure. During inflation, quantum zero-point fluctuations of the scalar field are rapidly stretched by spatial expansion to macroscopic wavelengths, freezing into classical density perturbations. These frozen quantum fluctuations created the tiny density variations 1 part in 100,000 recorded in the cosmic microwave background, which later collapsed under gravity to seed all galaxies, clusters, and filaments in the cosmic web. Thus, every massive structure in our galaxy, every star, planet, and organic molecule owes its ultimate physical existence to quantum jitter, amplified by cosmic inflation 13.8 billion years ago. Without these primordial quantum seeds stretched across space by inflationary dynamics, the universe would have collapsed into a featureless, uniform cloud of gas devoid of stars, galaxies, or life, demonstrating how quantum mechanics and cosmology are inextricably linked at the deepest structural level of reality. Analyzing the quantum to classical transition during cosmic inflation demonstrates how microscopic zero-point energy established the large-scale structure of space. As the inflaton field, the density variation is less than 0.004, density variation is less than 0.004 rolled slowly down its potential energy slope. The density variation is less than 0.004 V. The density variation is less than 0.004. Quantum fluctuations were stretched beyond the inflationary horizon, freezing their amplitudes into classical spatial perturbations. When inflation ended through reheating, these scalar perturbations seeded the primordial density fluctuations. The density variation is less than 0.004. Density variation is less than 0.004. These microscopic density seeds subsequently grew under gravitational instability during the matter-dominated epoch, pulling hydrogen and helium gas into gravitational wells to form early stars, galaxies, and clusters. Thus, the massive filaments of the cosmic web and the sprawling disk of the Milky Way are direct macroscopic enlargements of subatomic quantum fluctuations generated during the first. The density variation is less than 0.00. Cosmic scale's density variation is less than 0.004 seconds of cosmic existence, linking quantum field theory directly to observational cosmology. Investigating the stochastic dynamics of inflation field rolling illustrates how quantum diffusion competes with classical motion. As the inflaton's scalar field, the density variation is less than 0.004, density variation is less than 0.004 rolls down its potential curve, the density variation is less than 0.004 V, the density variation is less than 0.004. Classical motion drives the field toward the potential minimum at rate. The density variation is less than 0.004 selomkil. Ray CVV. The density variation is less than 0.004 simultaneously. Quantum zero-point fluctuations introduce stochastic jumps. The density variation is less than 0.004 Q. Ray CH. The density variation is less than 0.004 during each Hubble time interval. The density variation is less than 0.004 T-Chestios. HBM. The density variation is less than 0.004. In regions where quantum jumps exceed classical rolling, the inflaton field moves upward on its potential curve, triggering renewed exponential expansion. This stochastic quantum diffusion creates a self-reproducing inflationary multiverse where new bubble universes are generated continuously, ensuring that while inflation ends locally in our region, it persists globally across infinite space-time. Moreover, eternal inflation establishes a fundamental paradigm shift in how cosmologists view probability and measure in physics. In a multiverse containing infinite bubble domains, every physical outcome occurs infinitely many t, leading to the cosmological measure problem. To calculate meaningful physical probabilities, theoretical physicists employ regularizations such as the causal diamond measure or light cone time cutoffs, demonstrating that our observable universe represents a typical local manifestation of inflationary physics within a vast ensemble of pocket realities. Furthermore, the continuous generation of bubble universes within eternal inflation implies that quantum thermal equilibrium is never reached globally. Each pocket domain undergoes its own thermodynamic evolution, producing regions where entropy increases locally, while the overarching multiverse maintains perpetual expansion. This cosmic architecture guarantees that physical existence remains infinitely dynamic, preventing universal heat death across global spacetime. Cosmic horizon crisis, causal disconnection and thermal isolation. As we look toward the far future of the cosmos, the relationship between the Milky Way and the surrounding universe is set to undergo a dramatic and irreversible collapse. In 1998, measurements of distant Type Ia supernovae revealed that the expansion of the universe is not slowing down under the inward pull of gravity as previously expected. Instead, the expansion of space is accelerating, driven by a repulsive property of empty space known as dark energy, or the cosmological constant. Dark energy currently accounts for approximately 68% of the total energy density of the universe, and its repulsive effect increases as the volume of space expands. This accelerating expansion introduces a slow-motion cosmological disaster known as the cosmic horizon crisis. Because the space between unbound galaxy clusters is expanding at an accelerating rate, the cosmological event horizon, the boundary defining the absolute limit of space from which light emitted today will ever be able to reach us in the future, is shrinking inward in moving coordinates. Galaxies that are currently visible in our night sky are being swept across this cosmological event horizon one by one, pushed away by the relentless acceleration of space. In roughly 100 billion years, the accelerating expansion driven by dark energy will have pulled every single external galaxy group and supercluster past our cosmological event horizon. The filaments of the cosmic web, the vast supervoids, the Liniakia supercluster, and all 2 trillion galaxies currently visible within our observable sphere will be swept beyond our physical reach. Their light will redshift to infinitely long wavelengths, dimming into absolute optical nothingness. The local group, which will have long since merged into the single elliptical galaxy Milkdromeda, will be left entirely alone in an empty, pitch-black void. This future state creates a profound philosophical and scientific paradox. Future generations of intelligent observers residing on planets within Milkdromeda 200 billion years from now will look out into the night sky with advanced telescopes and see absolutely nothing beyond their own galaxy. The intergalactic void surrounding Milkdromeda will be completely dark, cold, and empty, because all light from external galaxies will have been redshifted past detection limits. Future astronomers will have no observational evidence that other galaxies ever existed. If those future scientists construct cosmological models based strictly on their optical observations, they will conclude that their single elliptical galaxy represents the absolute entirety of physical existence. They will see no evidence of the Big Bang, because the cosmic microwave background will have redshifted to wavelengths longer than the diameter of their entire galaxy, becoming completely undetectable. They will see no evidence of cosmic expansion, because all surrounding galaxies will be gone. Their universe will appear static, eternal, and solitary, a single island of stars floating in an infinite dead void. The cognitive shift enforced by the cosmic horizon crisis is the realization of the temporal privilege of our current era. We live in a rare, golden cosmic window where the universe is old enough to have formed complex galaxies, heavy elements, and conscious observers, yet young enough that the light from 2 trillion external galaxies still reaches our eyes. We are able to map the Laniakea supercluster, trace the filaments of the cosmic web, and photograph the baby picture of the universe in the cosmic microwave background, only because we exist during the first 14 billion years of a cosmic journey that will stretch across trillions of years. Comparing the Milky Way to the future universe reveals that our home galaxy is doomed to absolute physical isolation. The vast structural networks that currently connect us to the broader universe are temporary arrangements, doomed to be severed by the relentless expansion of dark energy. The 100,000 light-years of our galactic disk will eventually be all that remains of our accessible reality. Everything else, every filament, every void, every distant supercluster will be permanently erased from our physical horizon, receding into an unreachable void beyond the speed of light. To analyze the thermodynamic evolution of dark energy acceleration, consider the equation of state parameter. The density variation is less than 0.004. Rapahosi, the density variation is less than 0.004. For a classical cosmological constant, the density variation is less than 0.004. 1. The density variation is less than 0.004, yielding a constant vacuum energy density that drives exponential spatial expansion. The density variation is less than 0.004. If dark energy instead behaves as phantom energy, the energy density of space increases over time, culminating in a big rip scenario where spatial acceleration becomes so violent that it tears apart superclusters, galaxies, solar systems, planets, and subatomic particles in a final singularity. However, assuming the density variation is less than 0.004 reams, the density variation is less than 0.004. Milkdromeda will remain gravitationally bound while the rest of the cosmos recedes behind the cosmological event horizon. Inside Milkdromeda, stellar evolution will continue across trillions of years, as low-mass red dwarf stars slowly burn through their hydrogen fuel. Eventually, after hundreds of trillions of years, even red dwarfs will exhaust their fuel, leaving behind white dwarfs, neutron stars, and black holes in a dark, cold galaxy. The cosmic horizon crisis ensures that this final thermal death of our galaxy will occur in total physical isolation, severed from the rest of the multiverse. Furthermore, this inevitable causal isolation highlights the transient nature of cosmic structure. The magnificent tapestry of the cosmic web with its filaments, sheets, and supervoids is a fleeting phase in cosmic history, existing only during the epoch when gravitational collapse competes with spatial expansion. As dark energy takes complete control of space-time, The filaments will stretch thin, galaxies will be pulled apart into isolated clusters, and the universe will transition into an era of extreme dilution, where matter is separated by cosmic horizons that no signal can ever cross. Deep evaluation of the thermodynamic fate of isolated galaxies in an accelerating universe highlights the long-term isolation of Milkdromeda. As dark energy drives all external superclusters beyond the cosmological horizon, our merged local galaxy will enter the degenerate era of cosmic history. Star formation will gradually decline as interstellar gas reservoirs are locked up in stellar remnants, white dwarfs, neutron stars, and brown dwarfs. Over TKLs exceeding the density variation is less than 0.00. Cosmic scales, density variation is less than 0.004 years. The last generation of low-mass red dwarf stars will burn through their remaining fuel and cool into dark black dwarfs. Subsequent stellar interactions will cause orbital decay and stellar collisions, while rare dynamical encounters will eject stars out into the intergalactic void. Eventually, after the density variation is less than 0.00 cosmic scales, density variation is less than 0.004 to the density variation is less than 0.00 cosmic scales. Density variation is less than 0.004 years. Supermassive black holes will absorb remaining stellar remnants before evaporating via Hawking radiation, leaving behind an extremely cold, diffuse gas of electrons, positrons, and low-energy photons isolated in absolute darkness. Evaluating the long-term quantum dynamics of isolated galaxies in an accelerating universe illuminates the era of black hole evaporation. Following the exhaustion of nuclear fuel in Milkdromeda after trillions of years, stellar remnants will gradually sink toward the galactic center via dynamical friction, coalescing into a central supermassive black hole exceeding billions of solar masses. Over TCLs ranging from the density variation is less than 0.00 cosmic scales, density variation is less than 0.004, to the density variation is less than 0.00 cosmic scales, density variation is less than 0.004 years. These supermassive black holes will undergo quantum evaporation via Hawking radiation. As black holes radiate thermal photons and subatomic particles into cold space, their mass shrinks until they explode in a final burst of energetic gamma rays, leaving behind an empty, ultra-dilute universe dominated by low-energy photons drifting across expanding space. Furthermore, analyzing the long-term quantum mechanical decay of isolated matter in Milkdromeda highlights the grand timeline of the universe. If grand unified theories are correct, protons will eventually undergo quantum decay via heavy X and Y. Gauge boson exchange with a half-life exceeding the density variation is less than 0.00 cosmic scales. Density variation is less than 0.004 years. Proton decay will slowly dissolve atomic nuclei within white dwarfs and cold planets, converting solid matter directly into energetic leptons and gamma-ray photons until all baryonic structures in our isolated galaxy vanish entirely. Moreover, evaluating the cosmic horizon crisis highlights the profound shift in cosmological observables across deep time. As acceleration continues, the angular size of CMB acoustic peaks will stretch beyond observable thresholds, leaving future Milkdromeda observers with a smooth, uninformative thermal background. The historical record of cosmic origins will be permanently erased, turning the early universe into an unobservable theoretical mystery. Universal ratio, the Milky Way's true fraction of reality. We have travelled across an observational scale spanning more than 60 orders of magnitude, stepping upward from our local stellar disk to the ultimate boundaries of physical space-time. To grasp the true proportion of our existence, we must now reassemble this cosmic ladder and calculate the definitive mathematical ratio of the Milky Way galaxy against the full hierarchy of the universe. We began on a terrestrial planet orbiting an ordinary yellow dwarf star, situated 27,000 light-years from the center of a spiral galaxy containing 400 billion suns. Across a span of 100,000 light-years, the Milky Way appeared as an insurmountable empire of stars. Yet, when placed within the local group, our galaxy was revealed to be merely one of two major islands in a 10 million light-year cluster. When placed within the Laniakea supercluster, the Milky Way was reduced to a single vector, moving along a 500 million light-year gravitational watershed. When placed within the cosmic web, our home galaxy became an invisible cell clinging to a micro-thin filament wrapped around a 300 million light-year supervoid. And when placed within the 93 billion light-year sphere of the observable universe, the entire Milky Way shrank to a single grain of sand buried within an Earth-sized planet of 2 trillion galaxies. Mathematically, the volume of the Milky Way's main stellar disk is roughly 2.5 times 10 to the 13th cubic light-years. The volume of the observable universe is approximately 3.5 T10 to the 31st cubic light-years. Dividing the volume of our home galaxy by the volume of the observable sphere yields a fraction of the density variation, is less than 0.0047 density variation, is less than 0.004 or 0.00000000000000007% of observable reality. If we include the minimum unobservable flat universe, that fraction drops below the density variation is less than 0.00 cosmic scales. Density variation is less than 0.004. And if we account for the infinite spatial topology of eternal inflation, the ratio becomes literally 0. This extreme mathematical insignificance forces a profound re-evaluation of human position and perspective. From a purely physical and spatial standpoint, the Milky Way is completely negligible. If our home galaxy, along with every star and planet inside it, were to instantly vanish from existence right now, the overall universe would not notice. The cosmic web would retain over 99.999999999% of its mass. The Laniakea supercluster would continue its gravitational flow virtually undisturbed, and the 2 trillion surrounding galaxies within our observable bubble would continue burning through their nuclear fuel, entirely oblivious to our disappearance. Yet, this physical insignificance is counterbalanced by an extraordinary cognitive paradox. The universe is vast, cold, dark, and overwhelmingly empty. The vast majority of space consists of near absolute vacuum, lethal radiation fields, scorching stellar cores, and crushing gravitational singularities. In all the vast expanse of the cosmic web across trillions of light-years of void and filament matter is almost universally sterile, locked in simple, thermodynamic and nuclear processes that repeat endlessly without awareness. It is only within rare, quiet, stable environments like the habitable zone of an unremarkable yellow star drifting through an outer arm of a spiral galaxy that matter has organized itself into complex self-replicating structures capable of conscious thought. Through human consciousness, the universe has developed the ability to observe its own structure, calculate its own geometry, map its own superclusters, and comprehend its own frightening scale. We are the mechanism through which the cosmos reflects upon its own existence. The Milky Way may be a microscopic speck in an infinite void, a single drop of water in a boundless ocean, but it is the specific drop of water that knows it exists. As we sit on our tiny terrestrial world, looking up at the faint glowing band of stars arching across our night sky, we are not merely looking out into deep space. We are looking out from a rare vantage point of awareness, peering through a temporary window of time at a universe that is stretching out into infinity. The true scale of the universe does not diminish the human experience, it elevates it. revealing that our tiny stellar home is a fragile, precious oasis of thought suspended within an infinite cosmic sea. Reflecting on this universal ratio reinforces the ultimate synthesis of astrophysics and human inquiry. The physical dimensions of space spanning light years, megaparsecs, and particle horizons are not mere abstract quantities. They define the grand arena in which fundamental laws of physics operate. From the quantum fluctuations of inflation to the gravitational dynamics of superclusters, every process has worked in unison across 13.8 billion years to shape the world we inhabit. Ultimately, measuring the scale of the universe compared with the Milky Way teaches us humility without despair. We are tiny, but we are connected to the grandest structures in existence through the shared language of physical law. As our telescopes look deeper into the cosmic night, capturing light from distant filaments and ancient horizons, we continue to expand our mental boundary, ensuring that while our physical presence remains tied to a single galaxy, our cognitive reach encompasses the entire cosmos. Synthesizing the universal ratio across all structural scales yields the final resolution of our cosmological journey. By evaluating the ratio of galactic volume to observable, unobservable, and inflationary volumes, human cognition achieves a precise mathematical calibration of its physical